Okay, I think we're recording. Let's take a look at balancing half reaction method for oxidation reduction reactions. So if you're looking at your notes, this is the last page. I believe it's part F. In this method, we're going to use the half reactions to generate the overall balanced reaction. So to first get that, we need to find out what's being oxidized and what's being reduced. So let's take a look at the example. That's example 1, which is balanced in acid. We have HNO2 and Cr2O7 minus 2, making chromium plus 3 and NO3 minus. So let's take a look at oxidation numbers. If we're looking at HNO2, we know that our O is a negative 2, our hydrogen a plus 1. That leaves our nitrogen to be a plus 3. We've got our chromium and our oxygen, again O being a minus 2. If that's 7 of them in the compound, times 2 is negative 14. We got to get to negative 2. That means we need a positive 12, and chromium, there's 2 of them, so each one must be a plus 6. We've got our Cr plus 3, so that's plus 3. We've got our oxygen at a negative 2 for nitrate, and that leaves the nitrogen to be a plus 5. So when we look at this, let me get another color. When we look at this, we have nitrogen going from a plus 3 to a plus 5. That is a loss of electrons, 2 electrons. We also have a chromium going from a plus 6 to a plus 3. That is a gain of electrons. So our first step is to identify, well, which one is the oxidation component. So let's look at oxidation. Okay, so which one's being oxidized? We have nitrogen going from a plus 3 to a plus 5. That's a loss of electrons. So let's write the species that contain the nitrogen. So we've got HNO2 going to NO3 minus. Now we're not going to worry about atoms not being present, like for example there's no hydrogen in the products right now. We're not going to worry about that yet. We'll make sure that we account for that in a moment. Again, we have the nitrogen going from a plus 3 to a plus 5. That is, we want to start this process by making sure we have the same number of atoms. So we have 1 nitrogen on the left, we have 1 nitrogen on the right. So there's 1 N undergoing this change, and it's a change of 2 electrons. Oxidation, we always write those electrons as a product, and in this case there are 2 of them being lost. Then we're going to use, if you look up here, we're going to look at the charge balance. Okay, we're going to look at the charge balance and then do a little balancing of charges. So if you notice, since this one was balanced in acid, we're going to be using the charge of an H plus to help balance our reaction. So on the left-hand side, HNO2 has no charge overall as a compound. Right now that's a 0 charge. And NO3 minus is a negative 1, and each electron is a negative, and there's 2 of them. That's a total of negative 3. So in order for these sides of the reaction to balance, we have to make sure that the charges are balanced. So if I go from a 0 to a negative 3, that's not balanced. If we're balancing an acid, we're going to add H pluses to get that balanced. So I need to add 3 more H pluses to the right-hand side so that the total now, with the addition of those plus 3, is now 0, same charge. If this side, let me do this in red, if this side had instead not been 0 but had been negative 1, we would have added 4 H pluses to try to get to, 4 H pluses to try to get to negative 1. Okay, I'm going to undo that so we don't confuse ourselves. Oh, that's a lot of undoing. I'm sorry, everyone. There's lots of little lines. Okay, there we go. Okay, we're back. All right, so we've balanced the charges. We balanced the number of atoms that are undergoing the change. Now it's a matter of trying to count up and make sure we have the rest of the atoms present that we need. So for example, we have 1 N on each side. We have 1 H on the left, but we have 3 on the right. And so we need to add water then to the opposite side, or to the side that needs the extra H's in order to balance that. So we need 2 more H's. The way we do that is just simply add 1 water as a reactant. And you'll notice whenever you do that, if it is indeed balanced, the O's will balance themselves. So here we've got 1 O in H2O, we've got 2 O's in HNO2, that's 3, and we have 3 on the right. All right, let's pick it up again now. So our oxidation reaction is balanced. Let's do then our reduction. Okay, our reduction step, we have Cr2O7 with a -2 charge, or a 2 minus, turning into chromium plus 3. Again, here we want to make sure that the number of chromiums undergoing that change are equal before we begin. So again, each one was going from a +6 to a +3, but it's going to happen 2 times. So we need to make sure that our chromiums are balanced first before we start this process. So now, because our chromiums are balanced, each chromium is going from a +6 down to a +3. So each one is undergoing a change of 3 electrons. Well, how many total electrons, therefore, do we have? That's 6 total electrons. Notice I'm writing them as reactants because in a reduction process, we're gaining electrons. So those 6 electrons are added to the 2 chromiums to make 2 chromiums that are each +3. Okay, now we're going to do charge balance again. So I'm looking at the entire side to see what the charge is. We've got 6 negatives in the electrons plus 2 negatives in the dichromate ion. That's a total of 8 negatives on the left-hand side. On the right-hand side, we have 2 chromiums. Each one is a +3. That's a total of +6. So now we're going to try to balance -8 with +6. Again, we're doing this in acid, so we're going to use H pluses to balance the charges. If I'm going from a -8 to a +6, that's a net difference of 14. So I've got to add 14 positive charges. Notice I'm adding it to the left-hand side now this time, so that when I add 14 positives and 8 negatives, I end up with +6. Notice here, again, the charge is not 0 on both sides, and that's okay. It just has to be the same. So as long as it's the same +6 and +6, it's balanced by charge. Then we got to count for the atoms. So you'll notice very clearly that there's no O's or H's on the right-hand side, so we need to balance those. So we just added 14 H's. Our method, again, for balancing H's is to add water. So I need some more water on the right-hand side. I'd need to add 7 of them in order to balance with those 14 that I added. And notice what happened in the process. We have 7 O's on the left. We have 7 O's on the right. It's balanced. So these are our 2 half reactions. They're balanced half reactions. We have the oxidation half and the reduction half. Now, if we want to get the overall redox reaction, we need to add them together. To do that, now we want to look at what's happening to the electrons. So here in the reduction, we have 6 electrons that need to be gained for this dichromate to be reduced, and the oxidation is only producing 2 electrons every reaction. Well, that's not balanced. So in order to balance that, we need the same number of electrons to be given off by the oxidation as are given off by, or as are received by the reduction. So that means the first reaction has to be multiplied by 3. In other words, we have to run that oxidation 3 times as much in order for us to get enough electrons for the reduction to be able to happen. So if we're going to multiply by 3, we multiply everything by 3. So I'm going to put a 3 in front of the H2O, a 3 in front of the HNO2, a 3 in front of the NO2, and now this 2 becomes a 6 electrons, and my 3 becomes a 9 H pluses. Now I should be ready to add. I've got electrons on opposite sides. We always want to make sure that our electrons are on opposite sides, and that'll happen if we have one oxidation and one reduction. If we add these reactions together, we can eliminate anything that's on opposite sides and equal. So the 6 electrons on both sides can be eliminated. Notice we've got 3 waters on the left. We have 7 on the right. So the net result is we're going to have 4 waters on the right-hand side. Whoops. We have 14 H pluses on the left. We have 9 of them on the right. The net result is 5 H pluses on the left. And then everything else that doesn't cancel. Our HNO2, our dichromate, Cr2O7, -2. And then on the right side, we still have the 3 nitrates and our 2 chromium +3 ions. Just to check to make sure that it's balanced, we can go through and just do an eyeball check. We have 5 H's here plus one more makes 6. On the right-hand side, uh-oh, we have a problem. Whoops, I made a mistake. I caught myself. I forgot to include this 3HNO2. There we go. So I have 5 H's plus 3 H's. That's 8 H's on the left. I've got 8 H's on the right. I've got 3 N's on the left. I've got 3 N's on the right. I've got 2 chromiums, and then the O's, I've got 6 from the HNO2, plus 7 makes 13 O's. I've got 9 and 4, that's 13 O's. So there's my balanced reaction. Okay, now let's try the second example. This one is balanced in base. Again, we'll do the same process. Let's identify oxidation numbers first. Again, the sulfur is a -2 because that's what it says. Iodine, I2, is an element, so 0. Let's see again, oxygen is a -2. Typically, we multiply by 4, that's -8. We got to get to -2, so sulfur must be a +6. And then the iodine on the end, again, that negative means it's -1. So we should be able to identify from that which one is being oxidized, which one's reduced. We have sulfur going from a -2, do that in red, to a +6. -2 to +6, that's a huge oxidation. That's losing a ton of electrons. So that's our oxidation half. So let's start with our oxidation. I'll do this one in red because it'll be fun. So we've got sulfur going to SO4 with a -2 charge. Okay? We first check atoms to make sure that they are balanced, and they are balanced. There's one S on each side. And then we identify the number of electrons, right? It's going from a -2 to a +6. How many electrons must be lost in that process? Well, that's -2 down to 0, that's 2 electrons, and then 6 more, so that's a total of 8 electrons that are being lost. Again, we write it as a product because electrons are being given off by the oxidation. Then we check charge. So the whole left side is a -2 total. And if I add up the entire charge of the right side, that's -2 and 8 electrons, that's a total of -10. Now this particular problem says we're going to balance it in base. Well, base is our OH minus. So now, instead of using positives to balance charge, we're going to use negatives to balance charge, but the process is going to be the exact same. We're going to add negatives this time to make the two sides equal. So to go from -2 to -10, well, if I'm adding negatives, I have to add extra negatives on the left-hand side in order to make the negatives balance out. It looks like I need to add 8 hydroxides, 8 negatives, plus those extra 2 should end up being -10 total. So now my sides have the same charge. Then we do the same process. We're going to add waters to make sure that our hydrogens are balanced. Notice we just added a whole bunch of H's to the left-hand side, so we're going to add some waters to the right-hand side. So we have H2O on the right. How many do we need? Well, we just added 8 H's, so we need 4 waters to make that work. And again, take a look at your O's. 8 O's on the left, 4 in the sulfate, and 4 in the H2O. That means we've got 8 O's. We're balanced. We're good. Okay, let's try now the reduction. So let's look up to the actual reaction and see what's being reduced. We have iodine going from 0 to -1. Well, that's a gain of electrons. So I2 going to I minus. Again, first step is to identify how many atoms are undergoing that change. We've got 2 iodines on the left, so we're going to use a 2 on the right to make sure we have the same number of iodines. Again, we identified that iodine I2 is a 0 and that I minus is a -1. So how many electrons are being gained? Well, each iodine is going from 0 to -1, so now that's 2 total electrons. Now we check charges. Ooh, look, 2 negatives on the left, 2 negatives on the right. It's balanced. So this is the reduction reaction. We don't have to do anything else. Now we're ready to add the reactions together. We do this we'll do blue this time. So how many electrons are being given off by the oxidation? There's 8 electrons being given off, but each reaction for iodine is only using 2 electrons in the reduction. So we need to get these to be equal. In other words, we can't spit out a whole bunch of electrons and have them go nowhere. They have to go somewhere, and they need to go into the reduction. In order to make this work, we need to multiply the reduction reaction by 4 to make sure we have the same number of electrons being lost as are being gained. That turns the 2 into an 8, my iodine I2 into a 4, and my I minus iodide into an 8 as well. And then we should be primed to add. Now we have 8 electrons. Here, I'll do this in black. Now we have 8 electrons on the left and right. They will cancel, and we can add down. So let's add straight down. Do we have any hydroxides that are going to cancel? Nope. There's no other source of hydroxide, so we get 8 OH minus, plus we have our 4 I2 and our S minus 2. That's all going to make on the left side. So that's all the left side. On the right side, we'll have 8. Whoops. That was supposed to be an 8. Let me undo that. We'll have 8 I minus and an SO4 minus 2 and 4 H2Os. Let's just check. Let's just inspect to make sure we have it balanced. We have 8 O's on the left. There are 4 and 4 O's on the right. We have 8 H's on the left. We have 4 times 2, 8 H's on the right. We've got 8 iodines on the left, 8 iodines on the right, 1 sulfur, 1 sulfur. It's balanced. Okay, there you go. That's the half reaction method. Best of luck.